Hi, so this is the project for Team Responsible AGI for the course Responsible and Safe AI Systems. So, our project is called Harnessing Internal Representations, a universal strategy to counter adversarial attacks in machine learning. So, as an introduction to our project, as machine learning has been expanding more and more, the security and robustness of the AI models becomes more important. Our project essentially investigates a unique approach that leverages the internal representations of these inputs given to these AI models to enhance the resilience of these models against attacks. So, now you might ask, what is an adversarial attack? So, an adversarial attack is a type of threat against AI systems where maliciously modified inputs are fed into models to force incorrect or inappropriate behavior. These attacks cleverly disguise disturbances in data to undermine AI performance and pose severe risks. So, what's our hypothesis? So, we propose that the internal representations within AI models can differentiate adversarial inputs from benign ones. And this insight essentially lays the foundation of our entire strategy to build a robust defense framework against adversarial attacks. So here is an example of an attack. This attack is called the text fooler attack. And what it essentially does, it alters one word within a sentence, and that leads to a sentiment classification model misclassifying it. So as we can see here, the benign input is called the movie was great and I loved it. The adversarial input, which has one word changed, says the movie was terrific and I loved it. As you and I clearly know, this has not changed the sentiment of the sentence at all. They are both positive sentiment sentences. But this change is enough to fool the model into believing this is a negative sentiment. Another example of an attack is the deep word bug attack. What this attack does is it'll slightly alter the spelling of a word, and that is enough to fool the model again. So the benign input says this product is reliable, and the adversarial input just misspells reliable by swapping the I and the A. Again, as you and I know, this is not enough to make a sentiment difference, but the model is fooled by this. This is very clearly inappropriate behavior we don't want our models having, and we want to prevent this the best way we can. But why do we not use the existing methods? So, the existing method is essentially running a whole Distilbert model on top of your existing deployed model. This is very computationally heavy and affects the performance of your model a lot. We wanted to come up with a framework that is significantly more robust and lightweight, such that it can be used for any attack and on any model. So here's a basic approach and methodology of what our idea is. So what we do is we generate a data set of normal and adversarial examples using the attacks I mentioned before. So we essentially take, let's say, 500 positive sentences, run the attack on these sentences, and get their adversarial counterparts that are able to fool the model. Now, once we have these inputs, we conduct an analysis of the information encoded by each layer of the model we're thinking of using through probing each layer of that model and running logistic regression on the representations of the inputs to see how many it's able to classify as adversarial and how many as benign. Now, what we do is we use these inputs to build a steering vector that uses these representations from the most informed layer within the model, and we analyze the effectiveness of this steering vector in making an adversarial defense mechanism. So here is a probing analysis for the deep word bug attack on a Roberta SST2 model. As we can see, the highest accuracy is given by the seventh layer. So we take the representations of the benign and adversarial input pairs from the seventh layer. Similarly, for the textful attack, we can see that the last layer is the most informed layer and thus encodes the most adversarial information. So we take the representations of the adversarial and benign inputs from the last layer of this model. Now, once we have these benign and adversarial inputs, they're very clearly classified as two different sets. We say that if we take all these benign inputs and we average over them, and similarly take all the adversarial inputs and average over them, given enough data, the only thing we should be left with is the inherent benignness of an input and the inherent adversarialness of the input. Since we've given no constraints, we claim that this should simply encode benign and adversarial information. Now, if we subtract the adversarial information from the benign information, what we should be left with is what makes the adversarial information adversarial. what is that factor that can convert benign information into adversarial, and we theorize can convert back from the full adversarial input into benign. So as I said before, our first claim is that by averaging over all of our inputs, we get all rid of all the irrelevant data, and we are left with the inherent qualities of the benign and adversarial inputs. And our second claim is that we can use this information to create the steering vector, which can then correct the fool that the attack has created. So here are the results from our attacks. So we see that before 50, all 50 of the inputs are classified as adversarial, and none of them are classified as benign. But after we subtract this steering vector we've created from these adversarial representations, we see that we are able to get back 39 of these inputs into the benign space, which is almost 80% accuracy. Now, this was done on a dataset of 500 sentence pairs. If we increase this data, we should be able to see a jump in performance. But even without that, 80% is actually a very good accuracy. Thank you.